Okay, so we're going to look at gravity, and we're going to use some dynamics and look at some of the movement involving gravity, where gravity varies over distance, so gravity rate varies radially. Now if you do A-level physics, you'll already be aware of this formula here. So the force of gravity is equal to g, the gravitational constant, multiplied by m1, m2, all over r squared. m1 is one body and m2 is the second body. Now in certain situations we'll be looking at d rather than r, but they're basically the same thing. R is the radial separation. So force is equal to mass times gravity. We're used to that one. We've been using that. But now in this case we'll take g, m1, m2 over r squared to equal mg. Now if we do a little bit of rearranging, then we can redefine this gravitational constant as g. The two m's here will cancel. Okay, they're the same m. So g r squared over m gives us a way of defining this gravitational constant. So g is 9.8. R squared is the radius of the Earth, and m the mass of the Earth. This m here is the mass of the body that's interacting with the gravity of the Earth, which is equal to this second mass here. So when we look at a simple problem that can help us to redefine certain structures, certain systems, we can say that mg, the weight that we're normally used to using, is equal to gm m over x squared. So I'm using x as a distance, so changing this from r, like you might use in physics, to x as a displacement. So the force is equal to some constant over x squared. Okay, so that's just saying that the gravitational force varies with x squared. The distance between the two bodies is x minus r. Okay, so the height of something is the distance from the centre minus the radius of the Earth. So if we say that f is equal to kx squared, then at the surface we can take our surface conditions with the force of gravity as mass times gravitational field strength. We can set x equal to the radius of the Earth, which is what puts us at the surface. We put those in, and then we can redefine this constant as k as mg over r squared. Now doing that helps us to get rid of some other constants and gives us a new definition for the force. Now I'm going to look at question 4 from exercise 3b from the Heinemann at Excel textbook. It's a bit of a beast. I'll just let you read it. Okay, pause it to read it. So we start off with basic ideas. Newton's second law: force is mass times acceleration. And we can use the formula that we derived, or that I derived in the last slide, to equal the force of gravity here. Now you can see that the masses will cancel. So we can define this acceleration as the differential of velocity. So if we differentiate velocity with respect to x, then we get v dv by dx is equal to minus g r squared over x squared. So we've got an acceleration that varies with x. So if we separate the variables here, we've got v dv, so we've got everything in terms of v this side, and we've got everything in terms of x this side once they're separated. Now these two will be constants. So if we keep these as constants, then we can integrate. The integral here becomes half v squared, and the integral here just becomes, this changes to a minus 1 over x, which cancels with that minus, and just leaves you with a over x term. Combine any constants into a constant of integration here, and then we can use our initial conditions to find what the constant of integration is. So if x is equal to the radius initially, okay, so we're looking at the launch of an object, the initial velocity is just u. We can substitute those in and we get this formula here. Okay, not too bad. So finding the constant, we've got constant in terms of u, g and r. Now the distance I'm going to use as x is equal to the height and the radius. Okay, so height capital X, distance x. Okay, and you'll notice with my beautiful handwriting they're very, very, very different. I'm just going to try and accentuate that a little bit for you. Where's my pen? Here's my pen. Make that a slightly more curvy X. Curvy. Okay. So we go back to our original formula with half v squared is equal to gr squared over x plus c, and we've got a constant c here now, and we can actually put the x equals to x plus r. So when we're looking to find the velocity at a particular height, where height's this capital X, that's easy enough to do. So to simplify this term to get the velocity at a particular height, we can multiply both sides by 2, so that's going to get rid of that half, it's going to put that 2 here, it's going to put that 2 here. We need to simplify this, so to simplify it, just multiplied everything by x plus r. Everything's multiplied by x plus r that wasn't already over x plus r. Expanding out the brackets, a couple of things cancel, so this stays the same. U squared x plus u squared r, yeah. Take away 2grx, take away 2gr squared, so the 2gr squareds cancel. Leaves us with just 3 terms over x plus r, and that's what goes back into this equation here. Okay. So v squared was just equal to this, and then obviously I've square rooted it to find v. So this is our final answer to the question, which was find an expression for the speed of the rocket when it's travelled a distance x meters. Okay, so that was quite a hard example. I hope you've understood it. Have a look through the textbook examples. The textbook example actually covers question 1 from the exercise. So with that and this, you should be alright. Basically, you may have to separate variables, and that's going to be quite a useful tool here. Okay, good luck.